There's something that you need to understand, sort of a basic property difference between ionic compounds and covalent compounds, which is very important. So let me bring up the next slide and I'll describe that on the light board. Okay, so very important to understand is that when you have covalent compounds, they can also be called molecular compounds. Molecular compounds have covalent bonds. They have relatively low melting points and boiling points. On the other hand, ionic compounds have relatively high melting and boiling points. And you need to understand why. So let me just kind of make a simple chart here, hopefully to explain this. And so here we have an example of a molecular compound. And so a molecular compound, I tend to call it a covalent compound. And so this is just a compound with covalent bonds between the atoms where the electrons are shared between the atoms. So the example here would be chlorine. And I want to compare that to, say, here an ionic compound. And so this will be the example I'm going to use is sodium chloride. So again, one of the key differences in their properties is that molecular compounds like diatomic chlorine here, they have relatively low melting points and boiling points. Well, here, ionic compounds like sodium chloride and other ionic compounds as well, they have relatively high melting points and boiling points. And so now you need to sort of understand why that's the case. So let me draw a quick picture of what chlorine would look like. Now, at room temperature, chlorine, diatomic chlorine, would be in the gaseous state. So let's imagine what it would look like if it got cold enough to solidify diatomic chlorine. What would that look like? So I'm going to draw a little picture here. So here's one chlorine atom bound to another. So this is a diatomic chlorine molecule. So keep in mind that here between these two atoms we have a shared pair of electrons that spends equal time around these two chlorine atoms. Here is another chlorine molecule. And here is another chlorine molecule. And so maybe in the solid chlorine here, so this is very cold to get solid chlorine, we have some more chlorine molecules that are nearby. And so what you can see is that you have two chlorine atoms stuck together in each of these molecules, but there's a little bit of space between the individual chlorine molecules. So let's talk about some of the attractions that occur between these different chlorine molecules. So here what I'm going to do is put in some little dots here. So we have a weak attraction here between this chlorine molecule and this chlorine molecule, and then we have a weak attraction between these two, and you can form these, or will form these weak attractions between the chlorine molecules. And so these attractions between the chlorine molecules, they kind of hold the chlorine molecules together when the chlorine molecules are in the solid state, but they're very weak attractions. So notably, these are weak attractions. They're easy to break. In other words, you don't need much energy or temperature to break the bonds. What are these called? These are called van der Waals attractions. They're also called dispersion forces. So I'll write forces here and attractions here. Now let's sort of look now, compare that to the ionic compound. So with the ionic compound, as you know already, you have sodium ions like this one bound to chloride ions like this, and you just alternate in all three dimensions of space these ions. So here I'm just now alternating in 2 dimensions, but you can also, if I could, draw sodium and chloride ions that go into and out of the board. And you can imagine you have these alternating sodium chloride ions in a crystal. Now let's talk about the bonds that are there we've drawn here. So again, we have sodium ions stuck to chloride ions, and you might remember that the reason why that occurred is because sodium lost an electron with the chlorine, and then the sodium ion stuck to the chloride ion. And so this bond here is a strong one between the sodium and the chloride ions. And so this is an ionic bond. Okay, now let me just kind of quickly go back to diatomic chlorine. And I kind of pointed out there were weak attractions between the molecules. But remember, we were kind of looking at the bond also between the chlorine atoms. And so remember, as I talk about that, that if you were to look at the bond between the chlorine atoms, that would be the covalent bond and be pretty strong. Okay, so now I want to give you some actual numbers from boiling points and melting points. So we have MP for melting point, BP for boiling point. So let me draw a little chart here. And so chlorine has a very low melting point. So its melting point is negative 101 degrees Celsius. So it can still be pretty cold to get chlorine solid and melt it into a liquid. And then it doesn't take much energy on top of that to get chlorine to boil. So its boiling point is a little bit higher than that. It's still pretty low temperature, negative 35 degrees Celsius. Now, how about sodium chloride? Sodium chloride, well, you already know it's a solid at room temperature, right? So what that tells you that its melting point, that temperature to change it from a solid to a liquid must be much higher than room temperature, and it is. So the melting point for sodium chloride is pretty high. It's 801 degrees Celsius. So you need to get it that hot to get sodium chloride to melt and the ions to move around each other. The boiling point of sodium, in other words, to get the ions in the liquid state to go off into space in gaseous form, will be 1,413 degrees Celsius. Okay, so why is it that molecular compounds have such low melting and boiling points compared to ionic compounds? It's pretty easy to understand. It's because imagine, as an example, you have these two compounds and it's super cold. Let's say it's at negative 200 degrees Celsius. Let's say you start warming up the environment. So when you get up to a temperature, when you're at negative 200, they're both solid, right? The chlorine here, the diatomic chlorine is a solid, and the sodium chloride is a solid. But if you were to warm from negative 200 to say negative 101, something starts happening. At that temperature, some of these bonds between the chlorine molecules break. Not all of them, but some of them break. And when that happens, then some of the chlorine molecules are loosened up and they can start moving around one another. If they're moving around one another, then they go into the liquid state. So at negative 101 degrees Celsius, it gets a little bit warmer than that, then chlorine molecules are now in the liquid state. Now, how about sodium chloride? The cold temperature of, say, a negative 101 degrees, what's going on with sodium chloride? Nothing. It's still a solid, right? And the reason is these bonds between the sodium chloride ions are so strong that they hold those ions together. They're vibrating in place, but the ions cannot move past one another. You're going to need a lot more energy and temperature to get these ions loosened up from one another so that they can move around each other and it becomes a liquid state. So you keep warming up these solids. Now you're at, say, negative 50, and so molecular chlorine here is still in the liquid state. But when you get it up to, say, negative 35 degrees Celsius, that's still a cold temperature, but at negative 35 degrees Celsius, then the remaining weak bonds break between the chlorine molecules. And once that happens at negative 35 degrees Celsius, liquid diatomic chlorine boils off into gaseous diatomic chlorine. Now, even that cold temperature, sodium chloride, it's still a solid, right? And again, it's because the bonds between the ions are just too strong and it holds the ions in place. So if you keep warming up these materials, you really have to get it super hot at 801 degrees Celsius. So that is enough, high enough temperature that is strong enough to break these ionic bonds between the sodium ion and the chlorine ions, and then once that happens, the ions can move around each other and the sodium chloride becomes a liquid. And then, by then, diatomic chlorine will be in the gaseous state. So you could warm it up further and you can get it to 1400 degrees Celsius, and then finally all the ionic bonds between the sodium and chloride ions will be broken, and then these ions will go off into the gaseous state. So in general, the reason why ionic compounds have much higher melting and boiling points is because the bonds between the ions are very strong and you need a high temperature to break them. In molecular compounds, the bonds that hold these molecules together are relatively weak, and so you don't need so much of a high temperature to break them to either turn into a liquid state or to break more of the bonds and turn it into a gaseous state. Okay, so we're going to move on now. Okay, so let me turn to the computer again. Let's answer this question, which we have on the screen here. It says, which of the following will have the lowest melting point? In other words, it will change from a solid to liquid at a very low temperature. So we have 4 compounds. We have sodium chloride, we have carbon tetrafluoride, we have magnesium oxide, and we have potassium fluoride. And we want to identify which of those 4 compounds will have the lowest melting point. So you might remember the way you distinguish these compounds in terms of melting and boiling point is to figure out, does the compound have ionic bonds between the ions, or is it a molecular compound with those weak attractions between the molecules? So the way you figure that out is ionic compounds are formed from metals and nonmetals, and molecular compounds are formed from nonmetals only. So if you have a compound and you see it's formed of a metal and a nonmetal, then you can say, well, there's going to be ionic bonds between those ions, and so it's going to have a relatively high melting point. That's the case. If they're all nonmetals, and then what will happen is that then the interactions between the different molecules will be pretty weak, and so that will have a relatively low melting point. So you basically have to sort of go through these 4 compounds and figure out if they're ionic or molecular compounds. So sodium chloride here, sodium is a metal here, chloride is a nonmetal here. So this is ionic compound, so we would expect this to have a relatively high melting point. How about carbon tetrafluoride? Well, carbon here is a nonmetal, fluorine is a nonmetal as well. And so here, if it's nonmetals bound to nonmetals, the compound is a molecular compound. So the interactions between the molecules should be weak in nature. And so it will have a pretty low melting point. And you can look at the other 2, magnesium oxide and potassium fluoride. And what you would figure out is in both cases, you have a metal bound to a nonmetal. So these are ionic compounds, and therefore they would have relatively high melting points. So the one with the lowest melting point is the molecular compound, and so that will be carbon tetrafluoride. Okay.